Welcome to Empowered Learning. This is the second video in the series of videos that is going to introduce solving higher order ODEs based upon substitution techniques that we learned whenever we studied first order ODEs. So in the first video, what I went over was sort of the basic idea behind why we even do these types of why we even solve these types of equations this way, as well as outlining the different types of ODEs that we're looking at. And so I want to review that again quickly before we go into this second part here of this video. So the two main types of equations that we are learning how to solve in the series of videos here, of course, this first one here, which would be second order or higher ODEs that will only possess either x or derivatives up to whatever the order of the derivative is. The point here is that for these types of ODEs, you see no y shown in any term, okay? And so part one video was about that. Part two video will be about this type, where we see y, the first derivative of y, second derivative of y, if we're talking about second order. And let's say if we have third order, we would see y prime, y double prime, y triple prime, okay? The one thing that we don't see in these is we don't see any terms that have x explicitly stated in any term. And so that is what this particular video is going to be about, okay? Dealing with that. So now let's go review what the techniques we're going to use, or what the technique is that we're going to use to be able to solve these types of ODEs. So for these types of ODEs, remember here that we are not going to have any terms that will have an x showing, okay? So we won't have x showing in any of the terms. So because of that, we need to assume that our substitution variable, which is v, is going to be a function of y, okay? And so the reason for that is because if in our ODE, if we don't see an x there, then how can we say that what we're going to substitute here is going to be a function of x, okay? From what we see, there's no basis for us, no basis for us to do that, okay? So we take what we have available here, which is y, and we say let v be a function of y. Now we also say, all right, well, even though we're saying v is a function of y, we're also going to let the derivative of y with respect to x equal v. That's how we're going to define it, okay? And so by doing that, what that tells us is that although v is a function of y, v is actually a composition function, okay? And so, of course, whenever we take the derivative of a composition function, we are actually doing the chain rule. And this note that I have here is just basically trying to illuminate that fact. So when we make this substitution, we say here that v is going to be a function of y, and we said that d is going to be dy over dx. Now, one thing I want to note is whenever we are using this particular strategy, it's real important to leave your derivatives in the Leibniz notation instead of the prime notation, because it gets a little confusing if you try to write everything in prime notation, okay? So here we're going to say, of course, v is a function of y. It's going to be dy over dx. And then here we need to take the derivative of v with respect to x, okay? So if we do that, of course, we know that we're going to have to use the chain rule. So this is just me actually kind of going in a primitive way to form it, because this is literally what the chain rule would be. This is what you know it as here, but this is how we're actually able to do it. And then, of course, here when we switch the two, the dx and the dy here in the denominator, we see that dy over dx here that's just going to be representative of v because that's what we defined it to be. Okay. So here, the main thing to remember is that v is going to be dy over dx, but dv over dx, which is going to be, I guess you could say y prime, but not really, because y prime would actually be dv over dy, which is what you see here. And so that's why I'm saying that it's kind of best to leave it like this so that you don't get it confused. But dv over dx is equal to dv over dy times dv, okay? And so we basically take first derivative of y with respect to x, replace it with v, second derivative of y with respect to x, replace it with dv over dy times times v. And then, of course, from there, once we do the substitution, just like we talked about before in the part 1 video, what we end up with will either be separable, directly integrable, first order linear, first order homogeneous, first order Bernoulli, or first order with the ability to have a linear substitution. Okay. And then, of course, depending upon what type of equation it is, that lets us know how we're going to solve it. All right, so let's look at some examples. So now we're back to the example that we were at the start of this particular video. And if you recognize this example, it's probably because you watched the part 1 video, and this was the first example I did for that one. And so I want to call to your attention here that this particular ODE is one where we could solve using the technique that we use in the part 1 video as well as part 2. Okay. And so here I made a note here that all the examples in this particular subsection are going to be ODEs that do not contain X explicitly shown. Okay. So which means our ODEs are going to be autonomous. Now, the special thing that's going on with this particular one here is that, yes, we do not have X explicitly showing, but we don't have Y explicitly showing either. And so it was because of the fact that we did not have Y explicitly showing, we could solve it the way that we did in the part 1 video, which is basically let V be a function of X, let V prime be dy over dx, and then after that, let V be dy over dx. Sorry about that. Yep, so let V be dy over dx, and then we let V prime here be y double prime. Okay, so that's how we did it in part 1. So part 2, this video, what we're going to do is assume that V is going to be a function of Y. Okay, and then if we do that, we're also going to say let V also be dy over dx, but the way in which we come up with the derivative of V, or in other words, what V prime is going to be, this is going to be it's going to be dV over dy. So let me erase that. It's going to be dV over dy times dy over dx. Okay, and I'll go over this again, but here I'm just trying to make sure that you have an overall view of how the strategies are different here. Okay, now all the stuff that I'm saying here is just basically what I was telling you up there, but I'm trying not to read this verbatim. Okay, we also know that our solution to this ODE was this. So when we see this worked out again, we're going to make sure that we end up with the same thing. Okay. All right, so here, just like I said before, we're going to let V be a function of Y, but let V also be dy over dx, which we could call Y prime. Here, if we take the derivative of V with respect to X, that could be viewed as Y prime. But now note that what we have inside of here is a composition function, and we're going to have to take the derivative of this composition function by using the chain rule. Because although V is assumed to be a function of Y, we know that y is going to have to be a function of x, okay? And we know that because we said the derivative of y with respect to x. So that's an assumption that we have here, okay? So because of that, using the chain rule, the derivative of the function v with respect to x is going to be the derivative of a function v with respect to y times derivative of the inside function, which is y with respect to x. And so we remember here that dy over dx is just going to be v. So here we know that our y double prime is just going to end up being dv over dy times v, okay? So to make it real short here, this is what we need to do. Everywhere where you see y prime, replace it with v. Everywhere where you see y double prime, replace it with dv over dy times v, okay? And this will be true every time you employ this particular technique by solving an autonomous higher order differential equation and you use a substitution technique. And granted that it'll actually work. Okay. All right, so moving forward here, we make the proper substitutions. Y prime is v, y double prime is dv over dy times v. And if you notice, after some algebraic manipulation here, we realize that what we're dealing with here is going to be a separable equation, okay? Now, I don't necessarily have it in separable form, but I see enough to know here that I can get it in separable form. And so once I get to this point after doing some algebraic manipulation, you see that it is in separable form. And of course, from there, I would just integrate both sides. And so when we integrate the left side, it'll just be v cubed over 3. And yeah, this is not right. This is being taking an integral with respect to y. This should actually be v here. So because I have it here. But of course, anyway, any derivative of v squared is going to be v cubed over 3. Any derivative of 1 dy is just going to be y plus the integration constant. And then here, just a matter of trying to get v by itself. And I get v by itself, and I go ahead and choose here to replace this constant 3c here by just a simple one named c1. Now, again, our goal is to solve for y, not v. So because of that, I realize, or I recall, that v is actually the derivative of y with respect to x. So I take the left side of this equation here and I let it equal dy over dx, which is what you see here. And then from that point, I need to do some rearranging again, because what you see here once we do that is another separable equation. And I need to be able to take the antiderivative again. So if I take the antiderivative of both sides or integrate both sides, on the left side here, I see that I can use substitution rule, okay? And I don't know why I did that. This is supposed to be C1, but I have C2 here. I guess I'm losing my constants here, so I'll go ahead and write this in. Yeah, this should be C1, and this should be C1 here. Yep, okay. And this should be a C1 here. All right. So hopefully that'll fix everything here. So of course from here, if I do my substitution and whatnot, I'll take the derivative of 3y plus c1, derivative of w with respect to y. So the derivative of 3y is just 3. Derivative of any constant is 0. Rearrange that, and then replace everything in terms of w. And so that's what I have here. On this side, of course, on the right side, that's relatively easy. It'll just be x plus some integration constant. And then from that point, once we actually execute the derivative of w raised to the negative 1/3, which is 3/2 w raised to the 2/3. Of course, times that 1/3 on the outside. We go and simplify what we can, and then it's just a matter of rewriting everything, algebraic manipulation to solve for y. And I won't bore you with the details on that. But what I will say is that your final answer actually ends up being this. And of course, that was the same thing that we had earlier. Okay. All right, so let's look at some more examples. So for this example, again, what we're looking for here is we see that y here, we don't see, well, I'll put it like this. So we have y prime and we have y double prime, okay? What we don't see here is x showing up explicitly in any term in our ODE. So because we don't see that, it wouldn't be smart for us to let v be a function of x here, okay? So since that wouldn't be smart, what we're going to do here is we're going to assume that v is a function of y. And remember that we said that we're still going to let v be dy over dx, okay, or y prime. So because of that, the suggestion here is we're going to let v equal y prime, okay? And that in turn means that if I wanted to figure out what y double prime is, that's just going to be dv over dy times dv, okay? So this is really dy over dx here from the chain rule, but we know it's going to be this way every time, so we just write it. So now that we have that, then that tells me that what I'm seeing here, my y double prime, and I'll use this in a different color here. So my y double prime is going to be this dv dy times v, and my y primes here and here are just going to be v, okay? So therefore my equation here is now going to look like dv over dy, that's dv over dy, times v equals v parentheses v minus 2, okay? And so from there, of course, if I was to rearrange this, I could have everything with, v on one side, everything with y on the other. So if I do that, I'll have dv times v over v times v minus 2 on the left, and I'll just have dy on the right. And that will just simplify to dv over v minus 2 dy. And of course, that is a separable equation. And for that, we can just integrate both sides with respect to, v on the left side, y on the right. So if I was to do this on the left, if I was using substitution rule, this would be just natural log of absolute value of v minus 2 equals integral of 1 dy is just going to be y. But notice here, both of these have integration constants, but I'm just going to add it here on the right to make life easy for myself, okay? All right, so at this point, it would seem easy for us to just say, oh, look, we have y right here. And let's just say here that y is just equal to natural log absolute value of v minus 2 minus c, and we're done, right? So that would seem obvious. However, what is v? Okay, if you remember, v is y prime, or the derivative of y with respect to x. And so here we're trying to find what y is in terms of its derivative here, okay? And that's not going to fly here because we need to know explicitly what y is in terms of x. sorry, yeah, in terms of x here, if we can get it there. So what we need to do at this point here is, even though we have y sitting here, we actually need to solve for v at this point, okay? Because if we know what v is, and we're going to know what y prime is. And if we know what y prime is, we can figure out what y is. So I'm going to go ahead and erase this, and then we're actually going to continue solving this particular problem. Okay, so to get v by itself here, we're going to have to find a way to get this v minus 2 out of the natural log function here. And so we know that by using our logarithm properties, basically changing this logarithmic equation into an exponential one, we can do what I am doing right here. These are absolute values. And of course, the left side of this would just be absolute value of v minus 2. The right side of this would be e raised to the y times e raised to the c, according to our exponential rules. And of course, from there, using what the definition of absolute value is, I could just say that this is v minus 2 is equal to plus or minus e raised to the c times e raised to the y, which could just be a times e raised to the y, where we have a is equal to plus or minus e to the c. And of course, plus or minus e to the c is a constant. We don't really care whether a is positive or negative, because we don't have any initial conditions here to worry about. So at this point, all this means here is that we have v is equal to a times e raised to the y plus 2, okay? So now we know what v is. But remember, v is y prime, or dy over dx, okay? So therefore, here we know that dy over dx is going to be equal to a times e raised to the y plus 2. And from here, we see that this would be separable, but we're going to have to rewrite it this way in order to get it into that form, okay? And of course, in this form, what you want to do is just go ahead and integrate both sides, okay? Now, on the right side, we don't have an issue, okay? That's relatively easy to do. On the left side, we got a bit of a problem, okay? This is not one of those types of functions to where, meaning 1 divided by constant times e raised to the y plus 2, all that in the denominator. That's not something that we can just take the antiderivative of straight up, okay? Now, we can use the substitution rule. If we use the substitution rule directly, meaning if I let all of my denominator here equal, let's say, u or w or something like that, what you're going to find out is that in doing the substitution and trying to get everything written in terms of that new variable, that you're going to end up having to do partial fraction expansion, okay? And we can do it, but we would like to have an easier way to kind of go about doing this. So what we're going to do here instead is we're going to propose that we're going to rewrite this in another way, okay? So here we're going to say let, and I'm just going to use everything except for the dy here, equal, well, I really shouldn't say let here. It's probably more like note. So all right, so note here that if I write this, I could multiply the numerator and denominator by 1, but I'm going to make it look like, let's see, I'm trying to think, should I do the whole thing or just the, yeah, so want to make it easy, so we'll just do this. Yep. Because I could have done it by the conjugate of this, but that's going to make it a little bit more complicated. So we'll just keep it easy and do it this way. So if we do it like this, then this will be e raised to the negative y. And whenever I take e raised to the negative y and multiply it times both of these terms, the first term will just give me a, because the e raised to the y times e raised to the negative y will give me e raised to the 0, and e raised to the 0 is 1. And of course, it'll give me plus 2 times e raised to the negative y here, okay? Now, it seems like I made something simple more complicated, but this actually helps me out here, okay? So now we're going to let u equal what the denominator is here. And if we do that, then we're going to see that the derivative of u is going to be, derivative of u with respect to y is going to be derivative of any constant is 0. So it's going to be 0 plus 2 times the derivative of e raised to the minus y with respect to y using the chain rule is just going to be a minus e raised to the minus y, which is just going to be basically minus 2 e raised to the minus y, which means that essentially here we have a negative 1/2 du is equal to, and I forgot to put the dy here, e raised to the minus y dy, okay? So now that you see that, if I go back in here and write dy, and then multiply this times dy here, then you see that negative 1/2 du could replace all of this. And of course, u here could replace the denominator. So I have a way to express everything in terms of u now, and that's what I was needing to do. Okay, so therefore, the integral of dy over a times e raised to the y plus 2 here, this is just going to be rewritten this way. Okay, and we know that because what we have here can be rewritten this way. Okay, and all of this, when I do my substitution here, it just ends up being this negative 1/2 du over u. And of course, if I take the antiderivative of that, it's just going to be a minus 1/2 natural log of absolute value of u. Okay, and of course here I'll go ahead and do the substitution for this. This will be u is just going to be a plus was it 2? Yeah, got that. 2 e raised to the minus y. All right, and so now we have what this left side should be. Okay, we already know what the right side can be, so we're pretty much on our way to the finish line here. And I'm going to go ahead and switch colors here to note that. So therefore, what we have here now, I'm going to rewrite this. It's just going to be left side minus 1/2 natural log absolute value of all this business here equals, and then of course on the right side that'll be x, and the integration constant for both the left and the right we'll just put on the right to make life simple. All right, so at this point here we just need to get to this y that's on the inside here. And so the first thing I'm going to do is I'm going to multiply both sides of this equation here by -2. So we'll go ahead and do that here. So I'm going to take this, multiply by -2 here, multiply by -2. All right, so if I do that, then this will just give me natural log absolute value, all the stuff here on the inside. And here I will just have -2x minus 2c. And of course, from here, I could form a, from this logarithmic equation, I can form an exponential one by essentially saying here that I'm going to make this exponential with basis e. And then from that, of course, the left side would just be everything that's inside the actual natural log argument. On the right side, I could rewrite this as e raised to the -2x times e raised to the -2c. And here, notice that from my absolute value properties here, that I could just rewrite this as a plus e raised to the a plus 2 times e raised to the -y is equal to plus or minus e raised to the -2c times e raised to the -2x, where all of this, the plus or minus e raised to the -2c, I'm going to allow that to be a constant. I'll just call it k here, e raised to the -2x, where k is going to be this business here, okay? So now that we are here, then I know that I can continue trying to solve for y here. So dealing with this and this now. So here I need to get y by itself. So of course I can subtract a from both sides here and then divide both sides by 2. And if I do that, I'll have e raised to the -y here. And this is k e raised to the -2x minus a, all of that divided by 2. Okay. And so from here, if I wanted to get y by itself here out of the exponent, I know that I could take the natural log of both sides to do that. So here, I'm going to rewrite this way. Okay. So we have that in play here, and of course this left side is just going to be minus y, and over here we'll keep everything as is. All right, so let's move down and try to finish this one up here. So like we said before, on the left side, natural log of e raised to the -y is just going to be -y. And over here, what I'm going to do now is keep this like this for now, but I'm going to rename these as some simpler constants later. And of course here, this would be a minus natural log. Oops, didn't mean to do the absolute value part there. This will be k e to the -2x minus this. And of course, at this point, for simplicity here, let's see, I'll say C1 equal k divided by 2, and let's let C2 equal minus a divided by 2. Okay. Then we'll have y is equal to minus C1e raised to the minus 2x plus C2. Okay. And then finally, we could leave this answer this way, or what you could do is take this understood minus 1, put it in the exponent here, and I'll write it both ways. Either way is correct, but it just kind of depends upon your preference. You could look at it this way. Okay, so either one of those answers would be correct here. And again, C1 and C2 are your integration constants that we got. And if we had initial conditions, we would be able to find out what C1 and C2 are. So again, either version of this final answer here will work. All right, so this time let's look at an example where we actually have an initial value problem. So again, if you notice here, we have terms that have y, y prime, y double prime. But what we don't see is terms with x explicitly stated. Okay. So since we don't see that, again, for the substitution that we want to do, it will not be prudent for us to let v be a function of x. Okay. So instead, we're going to assume that v is a function of y, because the lowest order that we see of any variable here is just y. Okay. So here we're going to let v be a function of y, but let it also equal the derivative of y with respect to x. Okay. Now, what we've talked about before, we know that if I take the derivative of y, okay, so in other words, this is y prime here. So if I want to find out what y double prime is, that's like me taking the derivative of this, and of course I'm going to have to use the chain rule, and we already know what that's going to come out to be. It's just going to be dv over dy times v. Okay, so since we already know that, I'm just going to let it be what it is, and we're just going to use it. All right, so now what we need to do is just make our substitutions here. So if we make these substitutions, then of course, where we see y, when we see y double prime here, we're going to replace that with dv dy over v, and where we see y prime here, we're going to replace that with v. All right, so this will give us 3y, and in place of y double prime, we're going to put derivative of v with respect to y times v. And then on the right side, this will be 2 times, in parentheses, y prime. That's just going to be v. So we'll just say that that's 2v, and that'll be 2v squared. All right, and so now we just need to try to rearrange this the best way that we can. This looks like it will be an equation that is separable. The first thing I see here is that I could divide both sides here by v. I could do that, so I'll go ahead and do that here, because that's low-hanging fruit. So this will be 3y times dv over dy is equal to 2v. And then, of course, I want everything with v on one side, everything with y on the other. And, of course, if I do some algebraic manipulation to do that, I'll get dv over 2v on the left, and I'll get dy over 3y on the right. All right, and so here, I think to make things a little bit easier for me here, I'm also just going to go ahead and multiply both sides by 2 so I can have all my constants on one side here. So that'll end up being just dv over v, which is equal to 2/3 dy over y, okay? And so at this point, I know that this truly is a separable equation here. I can integrate both sides. On the left side, I'm just going to have natural log of absolute value of v. On the right side, I'm going to have 2/3 natural log of absolute value of w. And we could say here that this is going to be plus some constant, okay? Well, actually, I could put it on the left here. That would probably make it a little bit easier, but I'll just keep it here and just work with it. All right, so at this point, what I want to do is make life as easy for myself so that I can solve for v here. So to do that, I want to try to get everything with the natural logs in it on the same side of the equation. So here what I could do is I could rewrite the right side of this to be natural log of y raised to the 2/3, so using those logarithm properties. And then I'm going to subtract natural log of y raised to the 2/3, absolute value of y raised to the 2/3 to both sides. So if I do that, what I'll end up getting is what you see here, and this will just be equal to some constant, okay? Now, using the logarithm properties here, I could rewrite this as natural log of absolute value of v over y raised to the 2/3 equals to a constant. And then from there, change this logarithmic equation to an exponential one. And this would just leave me with absolute value of v over y raised to the 2/3 equals e raised to the c. And from here, life is easy now because I can just use my absolute value properties here to say that v divided by y raised to the 2/3 is just going to be plus or minus e raised to the c, where I can just say all that is a, where a is equal to plus or minus e raised to the c here, okay? And thus, this means that v is going to be y raised to the 2/3 times a. And that's what we want because we wanted to be able to solve for v, okay? And so if you remember here, v is the same thing as y prime. So we'll go down some. Let's say, but v is equal to dy over dx. So therefore, dy over dx is going to be equal to everything that we see here on the right. And here we can do some algebraic manipulation here. So this will be dy over y raised to the 2/3. This would be a times dx. And this is the same as y raised to the negative 2/3 times dy over a times dx. And at that point, of course, you see that, again, this is a separable equation. Life is easy here because we can just go ahead and integrate both sides. In both instances, we can take the antiderivative of the integrand straight up. So we are cooking with Crisco now, ladies and gentlemen. So let's go ahead and finish up here. So if I do the antiderivative of y raised to the negative 2/3 dy, I'm going to write it out the long way just to make sure I don't mess up anything, because sometimes I do mess up on these things with the fractions whenever I don't write it out. And on the left side here, this is ax plus c. And of course, in the denominator here, that's just going to be 1/3. So 1 divided by 1/3 would just be 3. And this would be 3y raised to the 1/3 here. And this will be equal to a times x plus c. So at this point, we just need to get y by itself. Pretty simple to do. First thing that we can do is divide both sides of our equation by 3. And then after we do that, of course, we could take both sides of this equation and raise it to the power of 3. All right, so we'll go ahead and write that in here. And so now doing that, of course, the left side will just be y. The right side will be ax plus c, quantity cubed, over 3 cubed, which would just be 27. And so this would be our general solution. Okay. All right, so now that we know what our general solution is, we can now go and use our initial conditions. Okay. And I'll do the initial conditions here in a different color. So here now, let's say initial condition. And the first one that we had here was, I think it's y1 is 1. Yep. So this is our first one. When x is 1, y is 1. So here we have when x is 1, y is 1. And that would imply here y, this will be like y of 1. So this will just be 1 here equals a times 1 plus constant, all that raised to 3 over 27. And of course, if we look at this, if we multiply both sides by 27, we'll have 27 is basically equal to a plus c cubed. And of course, if we take the cube root of both sides here, this will be 3 is equal to a plus c. So that, we know relationship between a and c here. If we apply the next initial condition, then of course we'll get another equation in terms of a and c, and then we'll be able to find out what a and c are. So for our next initial condition, we're now going to apply, this one is y prime of 1 is equal to 9. So we need to find out what the derivative of y is with respect to x. And so I know I have it here. However, the issue here is that this is not defined explicitly in terms of x, and I could use it, but it's actually going to make things a little bit more difficult. So I'm actually just going to just figure out what the derivative is from here. So we'll say that derivative of y with respect to x. Of course, since this is a composition function, we'll use the chain rule. So chain rule says take the derivative of blah cubed, which will be 3 times everything that's on the inside there squared, and of course divided by the constant 27, times derivative of the inside function. The derivative of ax with respect to x is just a, and the derivative of any constant is 0. So that's what this is, and of course this will simplify to just 1/9. So derivative of y with respect to x is just going to be a divided by 9 times a plus c squared. All right, so now that we have that information here, we can go ahead and use our initial condition here. So therefore, y prime of 1 equals 9. This implies that if I'm looking here, y prime of whatever is going to give me 9. This is a divided by 9. X is 1 plus c squared, which this is just a divided by 9. Of course, all of this is just a. And if you remember here, a plus c is equal to 3. And of course, that tells us here, because since 3 squared is 9, that a is just equal to 9 here. So now that we know what a is, we can also find out what c is. So therefore, 3 is equal to a plus c, which is 9 plus c. So 3 minus 9 equals c. So c is minus 6. So now we have what our two integration constants are, and we can just plug them in. All right, so finally here, this lets us know that y of x is going to be ax plus c. I think I had this is cubed and then over 27. Read back up here. Yep. And my a is 9, so that'll be 9x. My c is minus 6. And that'll all be cubed all over 27. So that is one form of the answer. We could keep going a little further here to really try to break this down some more. So here, if I factor out a common factor of 3, and I'll have 3 times 3x minus 2, and all of that will be cubed. So we'll have a cube here and a cube there, all over 27. And of course, 3 cubed is the same as 27. So all of that will just reduce to 1. And what we have left here is just 3x minus 2 quantity cubed. And this is our final answer in simplified form. This is the particular solution. All right. Okay, so this will be the last example that we will cover here for this video. I'm going to cover the higher order ODEs and going through the process of solving those in a separate video. So for this one, I've already got it worked out, so we'll just kind of step through it. It's really kind of a combination of some of the other ones that we've done already, but I kind of want you to see it together. So, of course, the first thing that we need to think about here is the fact that we are solving this because we do see that we have y prime, and y double prime explicitly shown, but what we don't have here is x explicitly shown. We don't see that. So here that means that we are assuming that our substitution variable v is going to be a function of y, okay? And again, here's where y is explicitly shown, y prime and y double prime. So we let v be a function of y, and let v be defined as dy over dx. Then of course, if dy over dx is y prime, then of course we would want to find y double prime, which is the derivative of v with respect to x. And of course, since v is a function of y, we have to use a chain rule. And so we know that y double prime just ends up being dv over dy times v. And so you see here, we actually make those substitutions. So in place of y double prime here, we are putting dv over dy times v. In place of y prime here, we're just putting v. Okay. And then of course from that, notice that at this point, I'm recognizing that this can be a separable equation. So I rearrange everything here to get everything with y on one side, everything with v on the other. From there, of course, I just integrate both sides with respect to v on the left, with respect to y on the right. Get this equation here. And right now, remember that my goal is to solve for v, okay? If I try to rush this and solve for y, what's going to end up happening is that I'm going to have y defined in terms of v, but v is y prime, or dy over dx. So I'm going to have the original function being defined in terms of derivative, and that's not something that I want, okay? So here we explicitly solve for v so that we can recognize that v is the same thing as y prime, or dy over dx. So we replace v with that. And then, of course, once we algebraically manipulate this equation around, we see that it's separable. If you notice here, we have 1 divided by e raised to the negative y plus some constant c. And just like in one of the earlier examples that we did, we see that taking the antiderivative of this straight up isn't really easy, but we can rewrite it. And the other problem that we had, I think we actually had something like ae raised to the y plus 2, something like this, and we ended up multiplying the numerator and denominator by e raised to the minus y. So here, since this is with a negative exponent, we want to multiply this, since it's kind of looking something like this, we want to multiply both numerator and denominator by e raised to the positive y, so that in the denominator, this first term here will just be a constant. So kind of getting back on track to what our actual example was, this is what we're looking at here. And we want to take this expression here and rewrite it by multiplying by 1, by making 1 look like e raised to the y divided by itself. And of course, you see that if we do that, then we have the situation here. And if I let this be my substitution, and I'm letting my substitution variable be u, then of course, when I take the derivative of that, I'll have a way to be able to replace e raised to the y times dy in terms of u. And of course, you see that happening here. And then from there, I go ahead and substitute everything in. So if you're looking here, the dy over e raised to the minus y plus c equals dx. On the left side here, I replace all that in terms of u based upon what I found here. The right side, not much to deal with. And to make life a little easier for myself, I also multiplied both sides of this equation by c. Okay. So once that was done here, of course, antiderivative of 1 over u du is just natural log absolute value of u. Antiderivative of constant times dx is just going to be that constant times x plus integration constant. This next step here, we realize that our substitution for u, we're subbing that back in. So u was 1 plus c e raised to y. So we just substitute that back in. And here, I'm purposely dropping the absolute value signs here because of the fact that we know here that whatever this ends up being is going to have to be greater than 0. And that's just because we know that the domain of a natural log function, no matter what we plug in here, in order for it to be defined, it has to be positive. Okay, so we can drop those absolute value signs there because we know it's going to have to be that. Okay, and the issue here is that if we had like some other expression like ax minus b, or ay minus b, it would probably be different because things would be dependent upon both a and b to figure out where that result, and x, by the way, to figure out where that result is actually going to be, positive all the time. But here, we know that e raised to the y must always be positive. We know 1 is always positive. And if this is going to work, then of course this constant here is also going to have to end up being, positive as well. Okay. So for those reasons, that's why I say that we're forced to have this case here. All right. So anyway, so from there, we can change this logarithmic equation to an exponential one by just making what I have here exponent raising to the same base. And then, of course, e raised to the natural log of whatever. It's just whatever. And over here, we can use our exponential rules to say that we can break this up here as e raised to the cx times e raised to the d, where e raised to the d is just some constant. And then from that point, it's just doing a bunch of algebra to try to manipulate this equation here to solve for y. And you can kind of follow along what I've done here to do that. But our general solution ends up looking like this. And so now at this point, since this was another initial value problem, we had some initial conditions. So the first one was that when x is 0, y is 0. And so, of course, we just plug that information in. And so, of course, with us actually plugging all that information in, notice here that if I was to plug in, let me do it here. If I was to plug in 0 here, then e raised to the c times 0 would be e raised to the 0, which is just 1. So that's why you see that 1 there. And of course, this ends up just being natural log of a minus 1 over c. And we can rewrite it like this using the logarithm rules. And then, of course, from there, we just say, all right, well, all this just equal to 0, which means if I add natural log of c to both sides, I have this. And then using my logarithm equation rules, I know here that whatever's on the inside of the logarithms must be the same. So that means that a has to be c plus 1. So if we apply the second initial condition, then of course here, notice that what I'm doing is I'm taking the function that I got here, and I'm rewriting it because I know I'm going to take the derivative of it. So I'll rewrite it in this fashion to make it a little bit easier for me to, kind of deal with. So by writing it like this, I don't have to worry about this term because I know that the derivative of any constant is 0. So I only have to worry about taking the derivative of the first term. And of course, I'm using the chain rule here. The derivative of natural log of blah is just 1 over blah times derivative of the inside function. And of course, I'll go ahead and take the derivative of the inside function. And of course, with this first term here, you'll be using the chain rule to be able to do that. Okay. All right. So now that all of that is done here, if you notice at this particular step, I'm actually done taking the derivative. But notice here that I realize that the a that's here and here is the same as C plus 1. So I go ahead and I plug that in. Okay. And so now the only constant that I have here is C. So once I plug in what X and Y are in this case, I should be able to find out what C is. So I know Y prime of 0 is 2. Everywhere where I see X, plug in 0. Result ends up being 2. And of course, you see with the simplification I was doing, eventually I get to the fact that C is just equal to 1. Okay. So if C is equal to 1 and A is equal to C plus 1, then it means that A has to be 2. So now we know what C is and we know what A is. We can plug that back into our equation here. A and C here, and of course for C there. And it just ends up being natural log of e raised to the 2x minus 1. Okay. And that is our final answer. And of course, that would be our particular solution for this particular initial value problem. All right, so that is the final example for the second order ODEs using the second technique where we end up having an autonomous type of equation. That means that no x's are showing explicitly anywhere in any of the terms. So we have to let our substitution variable be a function of y, kind of take derivatives and go from there. So this part 3 video that's coming next will be the one where I cover some examples of doing equations like these, but they are like of order 3, order 4, so that you can kind of get an idea of what that feels like. All right, see you in the next video.